Stop recommending popular stuff. Learn latent factors and personalize with matrix factorization. By the end, you will understand how a compact factor model uncovers hidden tastes and gives personalized top picks. I'm Professor Pi, teaching AI foundations with simple Python. Recommenders often show what is popular. That is safe but shallow. Real personalization finds the patterns behind why a user clicked or watched. Matrix factorization is a compact, powerful way to do that. It turns users and items into vectors. The inner product between those vectors predicts preference. Practitioners reach for it when they want scalable, interpretable recommendations with small models that still capture subtle tastes. Think of a movie app with a few hundred users and a few hundred titles. Each user has seen or not seen some movies. We want the system to guess the next movie a user will like. Success is better ranking on held-out interactions and useful top choices for a user. Matrix factorization works well on implicit data, like clicks or watches, and can be trained quickly with simple linear algebra. Intuitively, we are asking the model to explain a sparse interaction table with two low-dimensional matrices. Users get latent preference vectors. Items get latent attribute vectors. A high dot product means a good match. Strengths are compactness and speed. The main weakness is that it needs enough interaction data to learn meaningful vectors. We will build a tiny implicit recommender step by step. You will see raw interactions, a scoring function, a simple objective that treats any positive as a target of 1, a single pair gradient update, a regularized batch update, and finally, a top-end ranking for a user. No heavy libraries beyond NumPy are needed, and each step shows the core idea clearly. Now we will set up the smallest example to show the core idea. This snippet builds a tiny implicit dataset and initializes embeddings to score one user item pair. We create the matrix R to hold simple interaction counts, where any positive value means an implicit signal. The matrices U and V are user and item embeddings, randomly drawn with a fixed NumPy generator for reproducibility. We then compute a compatibility score for user 0 and item 2 using the dot product U0 and V2, which is the core idea in matrix factorization. Smaller random scales keep initial scores near 0, so learning has room to move. The printed init score shows the starting preference estimate before any training. Next, we will define the loss that tells the model what to fit. This code computes an implicit feedback objective that treats any positive in R as a preference target of 1. The variable P is a binary matrix marking observed interactions, and C is a confidence weight 1 plus alpha times the interaction strength. We get predictions with the matrix product U at V transpose. Then measure squared error weighted by C and averaged over all entries. The parameter alpha increases the emphasis on observed positives. Larger values push the model to fit clicked or watched items more aggressively. A higher loss 0 indicates our current embeddings poorly explain the positive signals and need learning. Now, we will make a focused update on a single observed pair to see learning in action. This example performs targeted stochastic gradient updates on one observed pair to move its score toward 1. We choose user U and item I, compute a confidence CUI from alpha and the interaction strength, and iterate a small loop. In each step, the error E is the weighted difference between the target 1 and the current dot product. We nudge the user vector UO in the direction of VI and the item vector VI toward UO, scaled by the learning rate LR. Increasing LR, or the number of steps, accelerates convergence, but risks overshooting and instability. A higher SO1 confirms the model is learning to favor that item for the user. Then, we will upgrade to a regularized batch update, so the model generalizes better. This snippet adds L2 regularization and a vectorized batch update to improve generalization. We first compute predictions pred and the weighted residuals E using the confidence matrix C and preference targets P. The user matrix U and item matrix V are updated in one step with gradients E at V and E transpose at U, while the term lam times U or V shrinks embeddings to avoid overfitting. We then recompute pred and evaluate the same weighted loss for a quick quality check. Larger lam compresses embeddings and can reduce variance at the cost of bias. A lower loss one signals a better fit after the regularized update. Finally, we will produce ranked recommendations for a specific user. This code ranks unseen items for a target user to produce top-end recommendations. We compute scores S as the dot product between the user embedding UU and all item embeddings in V. Interactions already present in R for that user are masked to negative infinity, so they cannot appear in the result. We sort scores descending with NumPy argsort on the negated values and slice the first two indices as IDX. Choosing a larger N returns more items, while still excluding anything the user has already consumed. The printed top N shows the model's current best personalized choices for that user. In a real project, the tiny example maps directly to larger matrices. Each user and each item become rows in U and V. Training sweeps over many observed pairs or uses efficient alternating least squares or stochastic updates. After training, the same ranking step produces live top-end recommendations for online or batch serving. Recap: matrix factorization represents users and items as vectors and uses dot products to predict preference. Use it when you have implicit interaction signals and want compact, fast models for personalized ranking. Caveat: it needs enough interaction variety to learn meaningful latent factors and benefits from regularization. Next step: tune the confidence parameter alpha to balance fitting positives versus noise, and measure top-end ranking quality on a held-out split. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.